Welcome back to the weekly Tech Digest for week of June 26, 2026. This week we cover 11 topics, including Helm Configmap Reload Cross-Release, Vibe Coding, HTML, and Generalized Visual Language Models, plus 8 more. Let's get into it. Updating a config map in Kubernetes does not automatically trigger a pod restart. This often leads to unexpected behaviors when applications hold config in memory. Understanding this can save you from deployment headaches. Kubernetes design means config map updates don't change the pod template spec. While useful for in-process file watchers, it becomes a trap for apps that read config at startup. Pods won't know about changes without a restart. A common solution is to add a checksum annotation to the pod template. This works well in monolithic charts, indicating to Kubernetes that a role is needed when the config map changes. But what if your architecture is more complex? In setups with multiple Helm releases, standard checksum patterns break down. Templating can't easily reach across releases, making it hard to recompute checksums for config maps. Always remember, multi-release systems can challenge single-release assumptions. Use checksum annotations deliberately, ensure you understand path mappings, and remember that a config map update doesn't guarantee a pod restart. What challenges have you faced with config maps in your projects? Vibe coding enables non-programmers to create software by interacting with large language models, also known as LLMs. This innovative practice makes software development accessible without prior programming knowledge, letting users generate code through prompts instead of manual coding. Vibe coding is particularly suitable for disposable software, meaning it is most effective for projects that are temporary in nature. The approach is optimal where the risks associated with low-quality code are manageable, making it a good choice for short-term or private applications. While vibe coding opens doors for non-programmers, it comes with significant risks. Applications created through this method can expose sensitive information and introduce security vulnerabilities due to the inherent nature of LLMs. There are concerns regarding the software functioning as intended. Vibe coding contrasts sharply with agentic programming. While both use LLMs for code generation, agentic programming places a strong emphasis on understanding and reviewing the generated code. Vibe coding, however, bypasses this crucial step, which can lead to potential risks. In summary, vibe coding empowers non-programmers to create software but comes with notable risks, particularly regarding software quality and security. It's essential to consider the implications of using LLMs for coding. What is your experience with using LLMs for coding, and what do you see as their biggest advantage or risk? Generalized visual language models enhance the interplay between visual signals and natural language understanding, significantly improving tasks like image captioning and visual question answering. Visual BERT effectively combines visual and textual input through a self-attention mechanism. It significantly improves performance on tasks like visual question answering, outperforming state-of-the-art methods on datasets such as NLVR and Flickr 30K. SimVLM introduces a prefix approach for visual and textual integration by processing images with bidirectional attention. This method significantly enhances performance in generating associated text in an autoregressive manner, outperforming traditional methods in ablation studies. CM3 extends multimodal applications beyond traditional limits by generating rich structured outputs and adapting to various tasks, such as image captioning and entity disambiguation, through effective prompt engineering. It benefits from a dataset size of 1 trillion. The frozen model fine-tunes visual embeddings without altering language model parameters. This approach allows for effective learning with limited training data, although fine-tuning has shown less effective results on visual question answering tasks. Traditional models rely heavily on separate object detection networks and are restricted to textual features. In contrast, generalized visual language models integrate visual and textual data directly, utilizing attention mechanisms for improved feature alignment. Generalized visual language models significantly enhance the interaction between visual and textual data, facilitating broader applications in AI. They present opportunities for more efficient learning, raising the question, How do you see generalized visual language models impacting future AI applications? Data generation techniques, particularly augmentation and language models, significantly enhance training datasets, especially when data is scarce. Data augmentation modifies existing samples to create new training points. Techniques like mix-up and cut-mix allow for synthetic examples while preserving semantic meaning. All four operations in exploratory data analysis help improve classification accuracy. Pre-trained models like GPT-3 can generate new data points effectively. By acting as a weak annotator, GPT-3 can provide labeled data at a fraction of the cost of human annotators, achieving 10 times cheaper than human labeling. Fine-tuning language models can yield high-quality synthetic training samples. The Lambda methodology trains classifiers alongside generative models to synthesize datasets, showing improvements in the low-cost regime. The process of language model-based data augmentation involves training a baseline classifier using the existing training dataset, fine-tuning a language model on the same dataset, and generating a labeled dataset from the fine-tuned language model. To summarize, data generation techniques like augmentation and language models enhance datasets, while GPT-3 offers a cost-effective labeling solution, and fine-tuning leads to high-quality synthetic samples. What are your thoughts on the reliability of data generated by language models compared to human-generated data? Active learning optimizes the selection of data to be labeled, significantly improving training efficiency in scenarios with limited labeled datasets. Active learning can enhance model performance with limited labeled data by intelligently selecting which data points to label, aiming to maximize model improvement per labeling cost. Uncertainty sampling is one of the primary strategies in active learning. It focuses on labeling examples for which the model is least certain, potentially gaining the most valuable information. Diversity sampling helps represent the broader data distribution. By ensuring selected data points are diverse, this approach improves model robustness across various input types. Hybrid approaches combine various sampling strategies for better results. They enhance the selection process by valuing different attributes of data points and combining various sampling preferences into one. MC dropout is an effective method for estimating model uncertainty. Utilizing dropout layers during inference allows for approximating uncertainty by treating the model like an ensemble of sub-models. In summary, active learning enhances training efficiency by selectively labeling data points, embracing uncertainty, and employing hybrid methods for superior results. What active learning strategies do you think would work best in specific real-world applications? Harness engineering enhances the reliability and quality of AI-generated code through structured feedback and guidance mechanisms. Harnessing a coding agent involves both feed-forward controls and feedback sensors. Feed-forward controls anticipate agent behavior to improve output quality, while feedback sensors observe outcomes to enable self-correction. Different execution types exist for guides and sensors. Computational guides are deterministic and fast, while inferential controls provide semantic analysis but are non-deterministic and slower. Regulation categories within harnessing facilitate maintaining the codebase's desired state. Categories include maintainability, architecture fitness, and behavior harness, each addressing different quality attributes of the code. The steering loop process involves identifying repeated issues in coding outputs and iterating on the harness to refine feedforward and feedback controls. In summary, harness engineering enhances AI output by combining feedforward and feedback mechanisms, empowering coding agents to self-correct and improving reliability. What challenges have you faced in implementing harness engineering in your coding workflows? Diffusion models represent a powerful new class of generative models that effectively learn to sample from complex data distributions by reversing a process of adding noise. Diffusion models leverage noise addition and removal. They define a Markov chain of steps, gradually adding Gaussian noise to inputs and learning to reconstruct outputs by reversing this noise process, inspired by non-equilibrium thermodynamics. The reverse diffusion process can generate samples from noise. By effectively estimating the probability distribution of states, diffusion models enable high-quality sampling corresponding to original data inputs, following the formula p_theta, x_0, t equals p, x_t, times a product over t. Parameterizing diffusion models is vital for performance. Key parameters like beta_t influence the variance schedule, which affects the sampling dynamics during both forward and reverse processes, where we see the relationship beta_1 is less than beta_2 and similarly for alpha_t. Diffusion models can be adapted for guided generation. Classifier-guided and classifier-free guidance techniques improve the quality of generated samples while maintaining diversity. Added techniques include glide, unclip, and imagine. Training speed and sample resolution can be improved. Techniques such as using fewer sampling steps and latent variable spaces can significantly reduce computation time while enhancing output quality. In summary, diffusion models use noise for sampling and can be adapted for guided generation, which improves the quality of outputs while maintaining diversity. What are the potential applications of diffusion models in real-world scenarios? Kubernetes operators like stack_gres and strimzi significantly enhance the management of stateful systems by automating recovery, backups, and configuration, showcasing clear advantages over traditional Helm charts. Operators provide superior management over stateful systems. Unlike Helm charts that set static configurations, operators continuously reconcile desired states. They handle operational complexities such as backups and recoveries, effectively encoding operational knowledge into a controller. Stack_gres simplifies backup management for PostgreSQL by supporting declarative backup configuration. This automation of backup lifecycle management ensures seamless integration with cloud credential injections. Strimzi facilitates Kafka management by effectively handling version compatibility. Its capabilities ensure that configurations are accurate for the versions of Kafka being used, particularly with changes from 3.x to 4.x. Operators automate certificate management and rotation using Strimzi Insert Manager. With this automation, certificate renewals occur without downtime or manual interventions, ensuring continuous availability. Declarative configurations streamline user and ACL management in Kafka. Kafka user custom resource definitions allow for easy management of authentication and authorization, synchronizing credentials without the need for manual edits to broker configurations. In summary, Kubernetes operators automate critical management tasks, providing clear advantages over Helm charts. Stack_gres and Strimzi specifically address the unique needs of PostgreSQL and Kafka, ensuring efficient and reliable operations. What challenges have you faced when transitioning from Helm charts to Kubernetes operators? Scaling laws provide a powerful framework for optimizing model size, dataset size, and compute in deep learning, allowing engineers to predict training loss and allocate resources effectively. Training loss decreases predictably with power laws. As model size, dataset size, and compute increase, training loss follows a power law curve, enabling estimation of resource requirements for larger models. A structured approach to predicting training loss involves fitting scaling laws on small runs and then extrapolating these findings to larger models. Optimal capacity allocation is crucial for model performance. Efficiency is maximized when model size and dataset size increase in tandem, with larger models requiring fewer data points to reach a given loss. Architectural details matter less than scale. The performance parameters of larger models are largely independent of architectural changes, indicating a stronger dependence on scale than design. Kaplan underestimated the optimal model size, proposing model size grows faster than dataset size. Chinchilla reversed this recommendation, emphasizing the proper training of large models with fixed compute budgets. To summarize, scaling laws help in predicting training loss effectively, Optimal capacity allocation is vital for model performance, and architectural details matter less than scale. How can scaling laws be applied to emerging model architectures to optimize their performance? Training large neural networks is a daunting task due to immense GPU memory requirements. As model architectures grow deeper and more complex, traditional single GPU solutions are insufficient. The stakes are high, as better models promise significant improvements in tasks like natural language processing. So how do we scale our training for these giant models? To effectively leverage multiple GPUs, we can employ various types of parallelism. Data parallelism copies model weights across GPUs and splits data for processing. Model parallelism, however, divides the model itself across devices. Lastly, pipeline parallelism elegantly combines both approaches, creating a more efficient workflow. Each method offers unique benefits and challenges. In addition to parallelism, several innovative memory-saving designs can help in training very large models. Techniques like activation recomputation save memory by recalculating outputs as needed. Mixed precision training allows for lower precision calculations, drastically reducing memory requirements. Offloading to the CPU further optimizes resources by moving less frequently used model parameters out of the GPU. A recent advance in scaling model size is the mixture of experts model. This approach combines multiple weak learners to create a stronger, more capable model. By dynamically selecting which experts to use during training, MO can lead to remarkable performance improvements while maintaining manageable resource requirements. In conclusion, efficiently training large neural networks involves a variety of parallelism strategies and optimization techniques. Whether leveraging data, model, or pipeline parallelism, or utilizing memory-saving innovations, each step can significantly improve performance. Lastly, exploring architectures like mixture of experts can yield even greater scalability. How will these advancements influence your next project? Contrastive representation learning enhances the learning of embeddings by optimizing the distance between similar and dissimilar sample pairs. This approach is crucial for both supervised and unsupervised AI applications. Contrastive loss minimizes the distance between similar pairs. It enhances embedding learning by ensuring that sample pairs from the same class are closer in the embedding space while maximizing the distance for dissimilar pairs. Triplet loss effectively improves model performance through hard negative mining. By selecting one positive and one negative sample, it allows the model to learn the relevant similarities and dissimilarities more effectively. Lifted structured loss improves computational efficiency in contrastive learning. This method leverages all pairwise edges in a training batch to enhance the quality of negative samples and streamline learning. NCE and InfoNCE optimize probabilistic representation learning. These techniques distinguish positive samples from negative samples, employing statistical modeling to enhance understanding between inputs. The soft nearest neighbors loss captures multi-sample similarities. By incorporating multiple positive samples, it refines the representation learning process across a diverse set of inputs. In summary, contrastive learning optimizes distances for effective embeddings and utilizes various loss functions which enhance learning. What challenges do you face when implementing contrastive learning in your projects? That's everything for this week's digest. Links to every post are in the description below. Drop a comment. Which topic did you find most useful this week? I'll see you next Friday.